Now, we studied about this part, right?
Yeah.
Now, generally what happens is you get a signal and you normally have to somehow amplify that signal, right? Because your signal could be very small, right? So let's say now you connect your output to a pre-amplifier. So then it amplifies the output, which is great. And ideally, you would want this amplifier to have a high gain and high noise rejection ratio, right? Ideally, yeah. Now here we have a divided negative feedback. So your output will then be what R2 over R plus 1. But Bobby, you work with plenty of amplifiers. Tell me, what's the problem here? When you connect your amplifier, there's also maybe some noise.
That there will be some noise introduced by the components and ICs in the amplifier.
That's right. So one of the things we should probably do is to analyze this noise from an amplifier side, right? So looking from
there is a non-inverting
plus, to be honest. Yeah. Okay. So if you look at the pre-amplifier noise, sorry, I should say pre-amplifier input noise, has three things. Okay, so
yeah, I see some sources.
Yes. So those sources is the equivalent in
noise
voltage. Yes. Oh, so you're talking about ER, correct, right? These ones.
So these are coming. These are the noise sources that you are representing.
Yes.
I mean, if you have a resistor that has some thermal noise, that is shown here. Okay, in the electrical.
Yes.
Okay. Yeah. Okay.
Because we went step by step, right? We considered the induction coil. Yeah. Then we considered the matching circuit.
Yes.
Now we are considering the preamplifier. Yeah. But each of these resistances, for example, have a noise source. Okay, so if you look at the preamplifier input noise, right? There are three components you need to consider. One is the
input noise of the op-amp itself.
Yes, input voltage noise. Then the input current noise. And your favorite thermal noise. So then you can write these three as then what? Vn squared In Z squared plus your thermal noise, which is 4kT R total squared.
What is Vn?
Vn is the input voltage noise.
Okay.
And then this is your input current.
Oh.
And this is your thermal.
Because in the equivalent circuit, it is written as EMI.
Where is that? EMI.
Op-amp.
INI, you mean?
INI is there?
Yeah.
EMI is also there, no?
No. ENI, you mean?
ENI.
Okay. ENI is just NPS.
Okay.
ENI, yes.
So the Vn, is it ENI?
No. So this ENI is this one here. And that's your thermal noise, which is all the resistances.
Okay.
And Vn is the input voltage, right? So input voltage, we don't have it here.
Oh.
So you're asking where this is, huh?
I'm a bit confused. VEN is the
the EN. Yeah, EN is the equivalent noise by the three sources: input voltage noise, input current noise, and thermal noise.
okay.
So that's this EN, huh?
Yeah.
Oh, okay.
For the op amp itself.
Yes.
That amplifier itself.
Yes.
Okay.
Yeah. So looking from this side
Hmm.
and looking to your left.
Yeah. So in that there is three components. One is due to that noise current.
Yes. One is a thermal component of
boiler resistance, and then the VN square, the first term,
is the input voltage.
input voltage. Yeah. I think that's what we have shown of ENI.
Here. Yes, to the amplifier.
Yeah.
Yes. Okay. You're saying okay. Yeah, this is this one here.
Yeah.
Correct. Yeah. So VN is not shown here, but yeah, ENI is. So basically we can write VN, right? Is in this case VN is equal to square, no?
Yeah.
Something like this, right? And what else do we have here that we have not talked about? Oh, Z. Z is the impedance of all the resistors that the input current noise passes. Is that right? So now I think we've covered everything here.
As far as the pre-amplifiers.
As far as the pre-amplifier is concerned, correct. Okay. Now, if you look at I wonder if I have another. I don't. Okay. So now, if you look at the noise that is generated by the input currents, right, of the pre-amplifier, flowing into the coil, like input current, pre-amplifier flowing into the coil. So, noise generated by the input current noise of the preamp flowing into the pipe.
Okay.
Then you have I N total is equal to. So then you have I N I Z squared plus I N I, the equivalent resistance squared. I N I here, okay, times Z plus I N I times the equivalent. Is the noise generated by the input current of the pre-amplifier flowing into the coil. Okay. Then, in this case, I'm gonna let me get up this.
So here, when you say R equivalent, what is that?
Yeah, that's what I'm talking about. Okay, so here, first we'll talk about Z. Here in this equation, okay? Z is what? Here, you have what? J omega L plus RL, okay? Then
RL or RC?
RC. This is going to be a continuing joke now. RC. Right? In parallel with 1 omega
by J omega C.
Yes, in parallel with
R naught.
Correct. Right? So your impedance, right? And your capacitive reactance, impedance.
So this is the impedance seen by the input of the amplifier when we look from this side.
Yes, I think that's a very good point, because I think you can very easily be confused.
Yeah.
If you don't know which way to look from.
Yeah.
So as you said, Boby, you said it's from the.
Yeah. So maybe we can consider this Thevenizing the circuit. So, I mean, all the sources will be replaced by its internal resistance.
Yes.
So that means here, these are voltage sources, so those will be short circuited.
Yes.
And then from the output, in this case, it's across R0.
Yes.
I look from that side, and R0, then 1 by j omega c, and RC plus j omega L. All of them are parallel.
Yes. Yes. Now, you also asked me what is this. Yeah. So in this case, this is R1 parallel to R2. Yeah.
So this current I N I is actually flowing through that Z, correct? Z, which is the equivalent resistance or impedance of that three elements.
Yes. You mean this one, and this one?
Yeah. All these together, and then entering into the other two, this R1 and R2 in one.
Yeah. First through this, and then entering this one and this one.
Yeah. So that is how maybe closest.
Oh. Yeah, exactly right. There's one more thing we need to consider in this equivalent circuit, and that's the thermal noise. Okay.
So here, if you want to keep the noise low, then these impedance values have to be small.
Say that again, sorry?
I mean, if I want the output due to noise low, we have to keep certain things low, this R equivalent. Or, I mean, let's say for the gain, if I choose to have for 1 plus R2 by R1, I may choose R2 10 times R1. Some ratio, let's say if I want gain of 11.
Okay.
Or more than 100, some ratio depending on gain I want. So now I can realize that using different values of resistors. For example, if ratio is 10, I can take
110.
Or 1K and 100 ohm.
Yes.
Or 10K and
yes.
So on.
Yes.
But that has an implication on the noise.
Yes.
That's what you are.
Yes. Okay. Yeah. So ideally, you would want to keep it what?
Yeah, noise should be low.
Yeah. So, but the resistance, you should want to keep it.
Yeah, but if the resistor value is very low, then the current flowing through that will also be more.
So there's a trade-off.
Yeah, because the op-amp may not be able to supply that much current.
Yeah. Then it's a problem.
Yeah. So we'll have to look at both aspects.
Yes. So somehow find a balance.
Yeah.
And the last thing we need to consider thermal noise, generated by basically all the resistors. So let's say Tn then becomes so you have we know this one 4 KTRL divided by plus j omega L times Z square. Again, looking from this side.
Yeah. So the 4 KT RC is the noise of the first source.
Yes. Of this one, no? Yeah. Okay. Now, do we have
So capacitor? Or there is no resistance there. So there is no.
Yeah.
It's an ideal capacitor that we write.
So we can forget about that.
Yeah.
Then we have R0 though.
Yeah.
But then again, what do we have? Square root of OKTRO divided by R0 times Z. Yeah. And there's one more. What is that?
This provided by the op-amp and the pre-amp.
Yes. Which we should also take into account. That's very simply 4kT. Square. So this is all the thermal noise generated by all the resistors. Something again we need to take into account. And that's
so you got this equation T. This is En or
this one,
the noise of the RC
here.
Noise of the RT, you are dividing with R plus j omega.
Here.
So that will become actually a current source. Correct, no? Voltage divided by
voltage divided by
that in RBS. So that's the current source.
Times the Z, which
which is So if you do that source conversion, our current source parallel to RL plus j omega L, parallel to 1 by j omega C, parallel to R naught.
Yes.
So that's why you wrote that Z there.
Here.
To Z.
Yes. Because as you said, right, this is
that's the current source. Multiplied by the whole impedance.
So this is a current
Thevenin impedance that gives you the voltage across.
Yeah. And this is of course your
Similarly for the other R naught.
This one?
Yeah.
And also the equivalent resistance is R1 and this. Yeah. Correct. So this is basic, a very, very, very basic analysis.
So this is how we will estimate.
Yes. Analysis of frequency.
Not so easy. Okay.
Remember,
I mean, once we know it, it's good.
Yeah.
Otherwise, I was not expecting this many equations hiding in this.
Yes, I mean, I still remember our first slide, right? We thought it was just a coil and they're changing magnetic field. But when we come to the applications, I think the students will get a clearer picture why we need to do all this analysis, right? Rather than just having a coil and just trying to measure a change in magnetic field. So that all this analysis we will become clearer later on as we talk about the applications. So, but we just talked about one coil, right? Now, if we have one coil, but we know the magnetic field has, let's say three axes, X, Y, Z. So in this case, what can we do? We have one coil in one dimension.
Right? So the output is just function of field going into that.
Right. But ideally, I mean, because the coil sensors are sensitive to magnetic fields, perpendicular, correct? Perpendicular to the main axis, as you said, this way. So in this case, what people generally do is you have 3 coils like this, right? Let's say for 3 different directions. Okay. And
so the component present in each direction will induce voltage in the corresponding coil.
Yes. And obviously, so you get your BX, BY, and B. This should be BZ measure. Okay. And obviously, if you want to get your scalar, you will get the magnitude of all 3 directions. You'll get a scalar component. This is something we'll talk about a little bit later, but this is interesting because, again, this was made in a lab. This is like a plastic kind of structure.
Mm-hmm. Some kind of bobbing.
Yes. And it was 3D printed. And then you have your windings here. So what I'm trying to say is, even I think students, if they're interested in building something, can be made. You can build something like this. And students now know how to analyze the equations behind the surge coil. So you can always build one at home or in the lab.
But I cannot measure earth magnetic field, no? Using this.
Why not? I think you can.
Earth magnetic field, because this is, see, all your equations are...
you're talking about DC.
Yeah.
Yes.
Yeah.
Earth magnetic field is DC.
Yeah.
So this is generally, this is something I was going to discuss towards the end, advantages and disadvantages.
Yeah.
But you're right. So
it's only for time verified, guys.
Or very low frequency to high frequency rather than DC magnetic fields. Unless you are moving this.
Correct.
That's
correct.
difficult, right? So this, what you see here, Yeah, so this is another way of, obviously, you can see the structure is different. You have a long core here, 3 long cores, again, with windings.
Okay.
But this, we'll talk about this a little bit later, but this is actually a surge coil system, a 3-axis surge coil system that was used in space, right? So you can make it at home, or you can make it for very niche applications. So I think it's one of the advantages of surge coils, and that's why you see surge coils used in a lot of different applications, because it can also measure a wide range of frequencies.